What we're going to try to do is just look at the three basic kinds of graphs we're going to see when we're handed a polar equation. The first kind we're going to see is the first kind you used to see when you first took algebra. It's one of the variables equals a constant. Remember that r is just a distance from the origin to the point, and if that's always a constant, all we get is a circle that's centered at the origin whose radius is r. That's it. Now remember, r could be negative, right? But that still works here. All right, the next thing we want to do is set the other variable equal to a constant, like that. Remembering that theta is always measured from this, let's go to theta, and now we want to pick every point that has that same theta. Well, that's this whole line. Now, when r is positive, I'll just get this ray. When r is negative, I'll just get this ray. But meanwhile, actually what we get is a line through the origin. So lines through the origin and equations of circles wind up very, very easy to graph, and they're very, very important because they both show up in science a lot. Now the third kind is where we have something that looks like r equals some sort of function of theta. I'm going to do what they usually do. You probably did this in Calc 2. I'm just going to do a nice easy example. This is usually the one that everyone does first. Looks like that. Now how are you supposed to graph that? You could plot lots of points, but that's actually slow and it's not nearly the best way to do it. The technique actually for doing this, I think was developed in the last 30 years, which is actually kind of cool. What we do is we graph first pretending that r is y and theta is x. So I'm just going to put like this. This is not the way we graph polar stuff, of course. It's going to look like that. 1 plus cosine theta just looks like cosine theta shifted up 1. So it goes all the way up to 2. Sometimes comes down to 0. It comes down like this. And then it repeats like that. And it takes 2 pi, and then it starts to repeat. So this graph, actually, whatever we're going to draw is going to repeat. Now, how are we going to draw this? Well, what I want to do, as much as possible, let's see here, how about if I do it just below it? Keep that right there. We're going to have to use the whole plane. So we'll go like this. This is still x and y, by the way, right? I mean, so we don't want to get too far away from that. Is first, try to plot the points correctly that correspond to the ones that are furthest away from the origin and closest away to the origin. For example, this point right here, it is the point 0, 2, but what that is the point theta is 0, r is 2. All right, well, okay, theta is 0, r is 2, looks just like that. Now, the next point I want to plot is the point pi 0. Pi 0, well, theta equals pi is pointing out this way, but 0 just gives me like that. And then I want to plot one more point. Then we'll start using the graph to actually get lots of other points. When theta is 2 pi, r is back to 2, so we're back out to here again. So far we only really have 2 points. Now, what we want to constantly do when we're doing this is compare to what would happen if r is constant. So for example, if I start at the beginning and r is constant, what I would get is something that just stays and looks like that. All right, let's see here. Pi over 2 is going to go right here. Yeah. Now, if it stayed constant, it would stay in that green line. But what happens is, as theta moves further and further out as it goes, right, r gets smaller and smaller. So for example, by the time I get to pi over 2, r is down to 1, right? So instead of staying out at 2 the whole time, it gets smaller and smaller and smaller and smaller and closer and closer and closer to the origin. And that continues to happen if I do something like 3 pi over 4 here. Right? Again, if this were to stay like this, right, it would look like this. But that's not what happens, right? We're getting an r that actually curves in. It keeps getting closer and closer to the origin as theta keeps getting bigger and bigger and bigger. So that's just going to come back all the way, come down here and look like that. Now what happens as r gets bigger and bigger and bigger? Well, as I get to, see, 3 pi over 2, 3 pi over 2 is at 1. Angle of 3 pi over 2 is pointing straight down, and I'm down to 1, so it's going to go like this. I have my other point. What happens between those times? Well, again, if this had stayed at this distance the whole time, it would look like that. So what we're going to get, yeah, let's make a few more dots so you can see what's going on, like that. Right? What we get is on R that gets closer and closer to that height. It's going to come out all like that. And at the very end, and again, I'm working a little bit backwards here. If this were always to be at 2, it would look like that. And so what we're going to get is as theta gets bigger and bigger, R gets bigger and bigger. So as theta gets bigger and bigger, it's going to get bigger. Theta moves over here like this, it gets bigger. Theta moves over here like this, it gets bigger. And you can see what I'm just going to get is a mirror reflection of the top part. Now, this should actually look exactly the same. There's lots of symmetry with cosine. This is called a cardioid. It's traditionally the one everyone does first, right? A cardioid is word for a heart, and sure enough, you can see it looks like a heart. But this does illustrate the basic technique, is that you graph R vertically, theta horizontally, and you get a graph that you can actually constantly use to piece together what the polar graph actually looks like.